Happy May Day, Physics Land! So, even though I am not here today, at least I'm not here as in, like, the building, I am at more fun and exciting, opportunities to professional develop, woo! Anyway, I miss you guys, and you get a little message instead of having the real void, but that will suffice. So, here are little notes and a little agenda of what we are going to do for today. First thing we're going to do is I'm going to give you back your impulse momentum variable quiz. I'm going to give you back your quiz. The marks are on there, your grades on there. And what I'd like you to do is to go through and work with me, and I'm going to kind of walk through the corrections on that. Then I want you to take a look at your formative exit check. That was from Friday. It was literally a problem that we had just whiteboarded. And I will have the answer on here. If you get an incomplete on either of those, you need to see me at the end of this week, or so Thursday or Friday when I come back, and work on developing an opportunity for you to retry that, do a retake. That's going to be a different question in a different quiz to make sure that you can get that grade up. After that, there's going to be a video on conservation of momentum and conservation of energy. All right, by this point you should have the sub should have given you back your quiz. If that has not happened yet, pause this video and please ask him or her to ensure that you have your quiz in hand, and then I'm going to walk through it with you and give you all the answers you need. So I'm going to give you a couple seconds right now to go do that. All right, so the idea of this now is that on this quiz you're supposed to go through and match these variables with this variable letter, so these names, these terms, with this variable representation. So let's start with this one. If we have T, well, T stands for time, so that should be number 11. Next one down, we have M. M is for mass. So we talk about a variable, M stands for mass. Meter is a unit, M is the variable. Delta T is your change in time, so that's going to be number 12. A is for acceleration, so number 1. F is for force. J, big J, this is one of the weird ones. J is actually impulse. So we talk about impulse and momentum quiz. We're talking about J. So impulse is 5. Next one down says MV. MV is actually representing just a single momentum. Just momentum. Not change in momentum, just MV. MV is a single snapshot of your momentum at a particular point in time. And P represents the exact same thing, actually. So when we talk about momentum, that is going to be P. So that is number 9. V is for velocity. V is for velocity. That's 13. And I have one quick addendum to what I had just put up here. When we have a J, yeah, J is for represents impulse. But remember that impulse is also equal to your change in momentum. So this could be, so besides 5, it could be your change in momentum, which is 10. Either one works, not a big deal if you get the other one. You pick one or the other. And then we move down to the exact same representation. Actually, F times delta T actually represents your impulse. And since impulse is also equal to your change in momentum, it could be 5 or 10. Now, this is actually looking at your momentum at one point minus your momentum at the next point. So final minus initial, which is then showing us that this is our PF minus PI, which is our change in momentum. So once again, it's the same idea. It could be impulse or change in momentum. They mean the same thing. They represent the same thing. They're equal in value, in other words. M times delta V. M times delta V is the exact same thing again. It's change in momentum or impulse. Same thing with PF minus PI. And And actually delta P is the same thing. Impulse or change in momentum. I know the last one's kind of nixed off a little bit there, but that's actually showing a delta V. And delta V represents our change in velocity, which is 14. So make sure you've made these corrections, and then, like I said, we'll have a retake option available, a different kind of quiz, but similar in nature. And you can hold on to this, actually, this quiz, and you can keep it in your folder. So once again, this was actually one of the questions that we whiteboarded. One of the questions we whiteboarded on Friday. And at the end of the hour, we had this check. This Friday's formative check. So at this point, if you have not received this yours back, please pause the video and then ask the sub to make sure to hand those out to everyone. And yeah, that will be the plan of attack for right now. Once you get yours back, take a little look at the solution here. The idea is we have this graph here. This graph is a force versus time graph. Okay, force versus time graph. Force versus time graph will give us then our momentum. But we get our momentum by finding the area under this curve. Force times delta T gives us area under this curve, which is going to give us impulse. And in this case, if you take 1/2 base times height, you get 2 Newton seconds for the impulse. But the key, though, is because it's negative 2 for the force, this is going to have to be a negative 2 Newton second impulse. In other words, my force is in the opposite direction that my object is moving, because it's moving in that positive direction at 12 meters per second. So the force then is in this opposite direction. And if it's in the opposite direction, we know initially it's going to be slowing it down. So once you know your impulse, you can go through and use your impulse and momentum equations. And by doing that, you're able to solve for your final momentum. These units are actually kilogram meters per second. So that's our final momentum. And you know your final momentum because you could find your initial momentum. The initial momentum, actually, this 1.8 kilogram meters per second comes from your mass times your velocity. So my mass is 0.15 times my initial velocity, which is 12 meters per second. And with that, we can find our initial momentum. Solve for your final momentum. And if I know my final momentum is equal to my mass times my final velocity, I can plug in my final momentum, plug in my mass, and solve for my VF. And when you do that, you get negative 1.3 meters per second as your final velocity. In other words, it was moving in the positive direction. The impulse caused it to slow down and then change direction. So it's now moving in the negative direction. You can hold on to this, and then once again, if you have an incomplete, please make sure to address that with me. Now, if you're done with all of that, your next task is me going through and looking at your conservation of momentum intro video. This is actually, it's an online YouTube video, so yay, you don't have to listen to Voight. But if you go over onto Blackboard, so you're going to go onto Blackboard, go under Impulse and Momentum, and under that point, you're going to see this intro video. Go on that intro video. I want you to watch it. I want you to please take notes. So go to Impulse Momentum, Conservation Momentum intro video. Watch that. Take notes. And once you're done, you can go show the sub your notes. And when you show the sub your notes, you'll be able to then get your homework assignment for the period. So please make sure and go and get that homework assignment after you have all the notes from this full video taken. So notes is your kind of your key, your kind of option, your way of your path to being able to get your notes. I'm sorry, getting your homework. Now wait, pause. If you haven't gotten you're not done with your notes quite yet, just pause and watch this after you're done. What I'm hoping to do is kind of summarize what that video says. We're talking about conservation of momentum. In other words, momentum is conserved. The momentum at the beginning is equal to the momentum at the end for collisions. Now, I draw pictures. Draw pictures is going to help you a lot. We have this before picture. We have this after picture. One quick note, you have two objects coming together. So one is going to have a positive velocity. One is going to have a negative velocity. That's a key part when it comes to setting up these problems. So I have my before and I have my after. Now, conservation of momentum says Pi equals Pf. And if you expand that out, what you actually get is your momentum at the beginning for object A plus your momentum for the object B at the beginning is equal to the momentum of object A at the end plus momentum of object B at the end, and you get this big long equation. And once you expand it out. Alright, so this is an equation that tells us our momentum at the beginning is equal to the momentum at the end. And this is true for all collision equations and all collision problems. And the way I remember this, here you're going to get a little voice singing, like tired, late singing of a song, but it's going to be good. MAVAI plus MBVBI equals MAVAF plus MBVBF. Woo! Conservation of momentum, a long equation, but really not that difficult, that complex. It's just breaking down momentum into different parts. And this is always going to be equal. Now, we also have another piece of this puzzle. Let me see if I can kind of draw a little line here. That was the conservation of mo. And now we also have another one involving energy. Energy is not always conserved. And this is specifically kinetic energy. Kinetic energy is not always conserved. Only on perfect bounces, which we'll talk more about. And perfect bounces we actually call elastic collisions. I'm going to actually go to the next slide and see if I can help out and expand on that. So, kinetic energy is not always conserved. In other words, you sometimes lose it. We've seen this when it came to our skater dude, right? When he was going back and forth, we saw him moving back and forth along that ramp. Eventually, in real life, he lost some of his energy into different forms, like thermal energy. Now, when it comes to a collision, though, and that's what we're talking about, collision energy. Collision can be lost because of a wide variety of different areas and different circumstances. When you have a collision, it can be lost because of the compression in the material, kind of like what we saw with the tennis ball. It can be lost through thermal energy, just like the skater dude for friction. It can be lost through vibrations, and we'll talk more about it tomorrow. But the idea then is that if it's not conserved, we call that an inelastic collision. Almost all collisions in real life don't actually conserve kinetic energy. They're not perfect bounces. Almost everything is going to be inelastic. But if these two values are equal to each other, we call that an elastic collision. Elastic collisions then, and in both of these we can determine if it's elastic or inelastic using this equation. Is the kinetic energy at the beginning equal to the kinetic energy at the end? Now we can expand that out. Kinetic energy at the beginning, when we have these two objects, and I know we had this before, when we have these two objects, we have object A coming towards object B. If we're talking about finding then our initial kinetic energy, we're going to be looking at finding the kinetic energy of this object A plus the kinetic energy of our object B at the beginning. Once they collide and they bounce off, we're then going to be looking at, okay, so we have this collision. We then have this after picture of object A and object B. And with that then we'll say, okay, if this initial kinetic energy is equal to my kinetic energy of A final plus my kinetic energy of B final, if it is, then it means that they're equal. Now the question then is, are they equal? So that question mark is what you're determining. If they are equal, like I said, they are going to be elastic, not equal, inelastic. And this is that full equation, that expanded equation. In other words, we just took our kinetic energy, 1/2 mass times velocity squared, and just threw some subscripts on it. Threw the A on it and the I, the B and the I, the A and the F, the B and the F. 1/2 mass A, VAI squared, plus 1/2 MB, VBI squared. Is it equal to 1/2 MA, VAF squared, plus 1/2 MB, VBF squared? Plug those values in. If it's equal on both sides, elastic. If it's not, inelastic. And now I want you to use those equations and complete your conservation of momentum problems, which the sub should be able to give you then. And you're going to want to do the front and back side. Front side is conservation of momentum. So on the front side, you're going to want to use that conservation of mo equation. And like I said, front side, your conservation of momentum equation. And on the back side, you're going to want to use your conservation of kinetic energy equation. And your goal then for that one is to determine, are they equal? Is this elastic or inelastic? And I'd like you to get this finished up then and work through that. And definitely work on this right now. And what I would like you to do is, by the time it hits 2:37, we'll say, apparently that's what my clock says, at 2:37, I want you to whiteboard these. And I want you to letter them off. A, B, C, D, E, F, G, H. And I want you to have each group work on one of these problems. So this is the front side, this is the back side. So work on those, whiteboard those. If you have time to present them, awesome. If you don't, put them on the side, over on the far wall where the number line is, and we'll go through those tomorrow. Otherwise, like I said, make sure you complete the worksheet for sure, so that by the time you get to class tomorrow, that is done. Thanks, you guys. Hopefully you're able to get through all this today, and yeah. Let me know if you have questions. Email me if you have any concerns. I will be checking my email throughout your class period. Thanks. And have a super awesome day.